Let us now go to the second and the last part of this chapter called learning. Now, in this second part, the first concept that we are going to learn is about the decision trees. We spoke about inductive learning in the previous video. Now, we'll talk about the learning decision trees. Now, decision trees, in fact, is something very easy to understand, because in a way, this is how we think as humans. But let us try and understand what exactly are decision trees and how do we go about making a decision with the help of a decision tree. Please observe this. Now, first and foremost, whenever I go to a decision trees, I'm going to make a decision based on the set of attributes that I use as inputs and the predicted output. What is the expected output? We'll look at that. What is the set of attributes which are available, which I'll take as input, and then accordingly we'll take a decision. There can be a Boolean or a binary classification as well. Maybe I can have a decision tree where I can take only two values, say yes or no, or true or false, and then go ahead. Now, as humans also, when we tend to think in the manner in which these decision trees work. So let us take up an example and then understand, and then maybe when you come back over here, you will be able to understand these points better once you've seen an example. Now, Boolean decision trees and the normal decision trees, the basic differences: my Boolean decision trees will have only two options everywhere. It's either yes or no, and then you take a decision. Like suppose if I'm waiting to cross a busy road, then I need to decide whether the signal is on or off. If it says, the pedestrian signal says walk, I walk. If it says no, I don't. That's it. I don't have a third option over here. Now, Boolean decision trees will give me only two options. But then if at all there are more than two options available, you can have the other decision trees as well. Let us try and understand this example. With the help of an example, we'll take up a simple decision tree. Suppose I and a group of my friends, we've gone to a restaurant. We now want to decide whether we have to eat or whether we want to eat at that restaurant or not. How do we go about developing a decision tree? There can be so many examples like this. Now, please look at this. Now, understand, I'm starting over here, and whenever I reach any of the leaf nodes, that is where I'll say I've reached a decision. It could either be yes to eating at that restaurant, or maybe a no, where I've decided not to eat at that particular restaurant. So basically, starting from the root node, if I reach any of the leaf nodes, that is where I've made my decision. Now observe this. When I reach a restaurant, I'll first have a look at the restaurant. Are there any patterns? If I find that there are no patterns, then I've decided not to eat there. If there are some people, some patrons, then yes, I'll eat at that particular restaurant. But suppose that restaurant is full at that moment. What do? I'll look at what is the estimated waiting time. Now, if it is more than say 60 minutes, no, I'm not interested in eating there. If it is between 30 and 60 minutes, which I still find is pretty high, so I'll think about the alternates that I have, the options that I have. If it is say 10 to 30 minutes, then I'll see whether I'm hungry enough, or can I wait for say about 30 minutes. Or if it is anything less than 10 minutes, I'm okay with it. I'll wait for that much time and then I'll eat at that restaurant. Now over here, if it is more than 60 minutes, I've got my answer. If it is less than 10 minutes, I've got my answer. But what if, say it was between 30 and 60 minutes? Then I'm checking, do I have an alternate? Suppose no, I don't have any alternate to that restaurant. So should I go ahead and make a reservation at the current restaurant? If I have an option, then I'll again think, is it a weekend by any chance? Because at any other place on a weekend, it might still be very difficult for me to find a table right away. So I'll look at this. If I try to make a reservation, then I need to look at the various options that I have. If I'm not planning to make a reservation, then should I go to the bar? If I'm planning to make a reservation, I'll just make a decision and stop. Similarly, if it's a weekend, accordingly, I'll take my decision further. If I'm hungry, I'll take my decision further. If it's raining, I'll take my decision further. So as humans also, we tend to start with a problem where we look at the options that we have, we look at the various inputs that we are getting, and then we try and develop a decision tree in our mind before we can actually reach to a root node. I can design an agent which develops a decision tree and goes ahead and tries to attain a solution by traversing the paths of a decision tree. So this is also the kind of decision making that is possible when you talk of agents in AI. The next type of learning is reinforcement learning. As the name suggests, reinforcement learning. Now please understand what exactly is happening. See, in the previous learning techniques, we spoke about what are the different ways in which the agent can think and then decide and then go ahead and make a decision. But over there, we were not bothered about the feedback that was happening or any kind of information which was given to us based on the decisions that we've already taken. Now, when I say reinforcement learning, if I design an agent which uses the idea of reinforcement learning, over here, the agent will look at the environment. It will automatically determine what is the best behavior, what is the best decision to be taken in that particular context, and then it will try and maximize its performance. But then, while it keeps doing so, what we'll keep doing is, as and when the agent keeps taking decision, as and when the agent keeps moving further, we'll keep on sending a little feedback to that particular agent about his behavior or about the performance of that agent. Now, this kind of feedback that we give is called as reinforcement signal, and this reinforcement signal will actually make my agent behave in a more efficient manner, because it will always be able to judge, or it will always be able to come to some conclusion about the decisions that it has taken, or about the way it has gone about making its decision. So reinforcement learning is again something which can actually help improve the performance of the agent on a consistent basis. Now, precisely depending on the environment for which you are designing the agent, depending on the problem that you are trying to solve using that agent, you will have to select the learning mechanism. There cannot be a specific rule that in this environment it has to be this, or in that environment it has to be that. It depends on the kind of environment that we are planning to work with and the kind of problem that we are trying to solve. Now, when you talk of reinforcement learning, as the reinforcement signal is given back, there are two different kinds of learners that I can design with the agent: passive learners and active learners. Now, what exactly are passive learners? Passive learners, basically, once they are being given the reinforcement signal, they will always record, they'll keep information about the utility of being in various states. So suppose they've gone from state A to state B, and from B to state C. In C they've received a reinforcement signal. Then they'll be able to record some information about what has happened in state B, or how good or bad it was in state B, and then the information is stored. Now, this information can be utilized or will be helpful when I try to solve the problem in, say, the next step, or maybe a new problem altogether. It won't influence my performance in the current problem solving mechanism. But in active learners, like what we discussed in case of intelligent agents, where we spoke about learning agents, where we spoke about the learning agents as the first part of this chapter as well, over here, the reinforcement signal is passed on to the problem generator, and within the same problem, the problem generator can still keep on evaluating its performances and still try to look for newer options, better options, and the more efficient options for the agent to continue working. So active learners, whatever information they receive, or whatever feedback they receive, or the reinforcement signal that they receive, they'll try and improve their current performance, and obviously they'll record it for the usage next time as well. Active learners will always be more efficient as compared to passive learners. So these are reinforcement learning. From the examination point of view, you can expect little short questions on these. So far in the papers, we've not seen major questions from say reinforcement learning, or maybe even ROte Learning. Now, what exactly is ROte Learning? ROte Learning, you can relate to it, because all of us at some stage in our lives have gone through ROte Learning. With children, you will see ROte Learning. ROte Learning is just by learning, just when you learn by repeating the same stuff over and over again. Like what we see with children, when you talk of nursery rhymes, they are being taught in such a manner, they just repeat it so many times that they eventually remember the nursery rhyme, but a lot of times they may not even be able to understand the meaning of what exactly they're talking about. Exactly the same thing can happen with agents as well. This is also called as the learning by repetition, because over here, basically what we try and do is we just try to memorize whatever we are looking at. It could be using so many different methods, maybe some learning aids, maybe some flashcards, maybe something else. Now this is where we will be able to just maybe ratify everything and then remember it and then implement it. Obviously, any kind of change or any kind of an uncertainty is not going to be tackled over here. This kind of learning will work only in a very specific environment, only in a situation where you don't expect any changes, but you cannot expect any kind of intelligence or any improved performance over a period of time in the system. So this is where the system will either be able to solve a problem or may not be able to solve the problem, because it has not come across those problems in its ROte learning process. One of the least efficient techniques that we have, but in systems which have a smaller problem domain where the environment doesn't change, ROte learning is one of the options that we have. So these are the various learning techniques that we can have. These are the various learning techniques that we can teach the agents or the system that we are designing, and we want them to behave like intelligent agents. So that's the chapter for us. That's the end of learning chapter for us. Thank you for learning with junkminds.com. Let's meet again with the next chapter. Till then, keep exploring, keep learning. Thank you.